What is up, guys? It's your boy Simon coming back with you guys for another video. Rewind. I did not do a video, so this is my first video. We're going to be talking about battery technology and a few of the things that come with it, the past of battery technology, how it's invented, right now what we're dealing with type of storage and renewable energy sources, and the future of possible newer kind of theory type of energy sources. So let's get into it. Hope you guys enjoy. Alright, so first slide, battery technology, the future of energy storage and renewable energy sources by Moi. So history of battery technology. It was invented by an Italian physicist, Alessandro Volta, who created the first battery by stacking alternate layers of zinc, brine, soap, pasteboard, or cloth, and copper. Now, through the process of oxidation, right here I can show you, through the process of oxidation, the negative electrode, zinc, loses electrons, and the reduction process causes the positive electrode, copper, to gain electrons and ionize in the water to produce hydrogen gas. Now, this solution here created this hydrogen gas, and through the process, this redox reaction, the wire created these electrons passing through it. And if you were to apply a bulb or some sort of energy, power kind of capacitor or something, it would take these electrons and it would use them, and it would light the bulb. And we know that this creates a current. And since the inventor's name was Alessandro Volta, we honor him by calling the energy storage by volts. Slide. And then since 1970, from the invention of the first lithium-ion battery, the battery in most electronics, the industry has slowly progressed to more effective products. Now we have Tesla, which has revolutionized the technology for vehicles and automotive industry. And through the new invention of different batteries, changes in different shapes and sizes kind of created different densities and quality of battery technology storage. Newer and more effective energy storage compartments, and there is a struggle to create an effective tool for containment and storage of energy. So now we have a lithium-ion. Now, different batteries today. Now, today we have lithium-ion, lithium-sulfur, and the solid-state batteries. All of them are different. Now, which one? What are they? The lithium-ion battery is the energy storage and release is provided by the movement of lithium ions from the positive to the negative electrode back and forth via the electrolyte. So there's a negative electrode and positive electrode, and let's go back. The positive electrode and negative electrode, and there's the electrons going through it, and that's going to allow there to be a charge and there to be a voltage going through the parts of the circuit in the battery. Positive electrode acts as the initial lithium source, and the negative electrode as a host for lithium. The advantages of this technology is lithium battery technology allows the highest level of energy density, very low self-discharge, and very long lifetime and cycling performance. Typically thousands of charging and discharging cycles. So usually different batteries that have low density, they can take a little bit of charge, and each time they discharge and charge, they lose a little bit of their efficiency. And that's a bit of a problem that we have to deal with, but creating a more high performance battery that doesn't lose energy through heat or through other types of materials, that's something we're trying to achieve. The expectation is that it will be ideal for use in applications such as energy storage systems for renewables and transportation, marine railways, aviation, and off-road mobility, and where high energy, high power, and safety is mandatory. Today we use a lot of those round cylinder type of batteries and those electrochemical batteries, but obviously we're trying to move into something a little bit more different than electrochemical and chemistry. Then there's lithium sulfur. In lithium sulfur Li-S batteries, there are no host structures. While discharging, the lithium anode is consumed and sulfur transported into a variety of chemical compounds during charging. The reverse process takes place. A lithium solution battery uses very light active material, sulfur, in the positive electrode and metallic lithium as the negative electrode. This is why its theoretical energy density is extraordinarily high, 4 times greater than that of a lithium ion. That makes a good fit for the aviation space industry. Obviously, the lighter the battery is and the more dense it is, the better it is for using it in space and for flight. There's a major technological barriers have already been overcome, and the maturity level is processing very quickly towards full-scale prototypes. Eventually, we're going to be able to see lithium sulfur commercially and full-scale prototypes, obviously, as well. There's solid state now, which is the more revolutionized, more technologically advanced type of battery, which we're looking more into. In all solid state batteries, the liquid electrolyte is replaced by solid compound, which nevertheless allows lithium ions to migrate within it. Solid electrolytes are non-flammable when heated, unlike their liquid counterparts. Second, it permits the use of innovative, high voltage, high capacity materials, enabling denser, lighter batteries with better shelf life as a result of reduced self-discharge. So it allows it to maintain that power capacity and density without each time it charges and discharges, doesn't really lose that quality of the battery. So expectations first will be a solid state batteries with graphite based anodes, bringing improved energy performance and safety. In time, lighter solid state battery technology uses a metallic lithium anode should become commercially available. Now, these are the questions that we have to ask ourselves to be able to really understand the future and how these battery technologies will help us deal with different situations and problems that may come. Right now, the technology is based off of lithium-ion batteries. Will we continue to upgrade the quality of the materials, or will we utilize quantum theory? Now, a lot of these batteries, the lithium-ion, the lithium-sulfur, and the solid state, all kind of have the same kind of electrochemical basis. They have this kind of the negative and the positive anode and cathode, and the wire that connects them and the electrolyte in between, basically. But what the main question we're trying to figure out is if it's possible to integrate more concepts that allow for quantum theory, things that allow us to migrate to smaller components and smaller technologies that will maybe allow greater density. Because right now we want to be able to find something that's cheap, light, and easy to use, and safe as well, of course. Then the other question is, the idea based behind battery technology is extremely electrochemical. Will we see a shift to ideas of physics and energy technology? That's a big one. We want to be able to move from electrochemical reactions, like redox reactions, to a more innovative and more technologically advanced physics reactions. Something that will kind of allow us to, like, for example, quantum theory or some other type of particle theory and stuff like that, that can be integrated for energy storage. What else is there? What are the impacts of high efficient energy storage of large quantities, and how it will be integrated? Now, here's examples of this. Gogoro, and these are the graphene. These are the lithium ion and lithium sulfur type technologies. They're flat and but they have high density. And here's this last question. This main thing is that there's a lot of solar panels and having these big batteries allowing to control and have a strong shelf life, keep these batteries in good condition without degrading them, is something we should be looking towards. And how it will be integrated is the idea of right now there's a lot of fossil fuels and coal has a very high energy storage because you can just leave it there for a long time, nothing will happen to it. But batteries and energy, such as electricity, is a little bit harder to maintain and store. And here's a Tesla battery. This is an example. It's not really flat. It's many different types of batteries that are all connected together in a huge, huge board. Now, here's some two videos I wanted to share with you guys, so you guys have a bit of an understanding of what the future looks like. So apart from electrical chemical reactions, the application of a sustainable nuclear energy battery or miniature sun capable of creating absurd amounts of clean energy may be the future of that technology. I here give you guys a bit of an overview.
Would you use a smartphone or electric vehicle powered by nuclear batteries? Or maybe a nuclear-powered pacemaker that never needs changing? Russian researchers developed a nuclear battery design based on a radioactive element that has a half-life of over 100 years. This means that any device having this nuclear battery won't need recharging for over a century. And that's not all. This battery produces 10 times the power of a traditional chemical cell. For people who use smartphones and other smart devices 24/7 and are tired of constant recharging, this might be good news. And let's be honest, that's most of us. What's better news is that there is no need to panic, because this nuclear battery does not contain any mini nuclear reactor inside it. So how does it work? nuclear batteries work through a process known as beta voltaics to produce electricity. As the name implies, it generates power from the decay of beta particles. A radioactive source inside the device decays and emits beta particles, and when these interact with a semiconductor layer, they can create an electric current. The prototype design is based on a radioactive isotope nickel-63 and a semiconductor made out of diamond. The nickel-63 isotope fires high-speed electrons into nickel foil, generating electricity. This nuclear battery boasts about 3,300 milliwatt-hours of power per gram and continues producing power for 100 years, because this is the length of nickel-63's half-life. Batteries powered by radioactive materials have been around for more than a century, before more advanced methods, such as lithium-ion, arrived. Previously, researchers developed a nuclear battery that used a radioactive isotope, strontium-90, that splits water molecules to produce electricity, and a nanotritium battery with a 20-year lifetime. This sort of technology would be ideal for powering things you can't, or would rather not, access often, such as pacemakers. Now, you might be thinking that carrying a mobile device 24/7 packed full of radioactive materials is a bad idea, especially because beta radiation can cause cancer and death. But beta radiation can be easily stopped with a thin piece of aluminum, and this makes beta radiation much easier to control. Just make sure that the beta voltaic nuclear battery casing is more than a couple of millimeters thick, and try not to drop it. Like, ever. Even though we can control beta radiations, it will be some time before we can see commercial nuclear batteries in the market. Marketing a nuclear-powered pacemaker in today's world would demand more than just a catchy news ad. A lot of public education needs to be done before potential customers will feel comfortable using this technology. For now, nuclear batteries will probably only be used in military and space applications. Space agencies planning long trips will need to develop small power sources that don't need replacing in order to save on cargo space. Still, it would be nice to have a smartphone that never once needs recharging.
And now, moving on to a miniature sun.
Imagine what it would be like to have a miniature version of our sun right here on Earth. Would this artificial star provide us with an infinite supply of clean energy? Would we even need all the coal and nuclear power plants that give us electricity today? Could the energy from a mini-sun replace rocket fuel? And could we control it? This is What If, and here's what would happen if we built a replica of the sun on Earth. The sun is an enormous nuclear fusion generator. Every second, it fuses 620 million tons of hydrogen into 606 million tons of helium in its core, releasing a vast amount of energy in the process. To create a replica of the sun on Earth, we just need to squeeze atoms of hydrogen hard enough to make them fuse. Shouldn't be too hard, right? Well, this fusion is only possible at extreme temperatures. Even the sun's coldest part, its surface, burns at an incredible 5,500 degrees. Not even a spacesuit could protect you from that kind of heat. But we could engineer a high-temperature superconductor to tame our scorching mini-sun. What would it take to bring this brighter future into reality? Having an artificial sun on our hands would provide us with almost limitless amounts of energy. Of course, it would be much smaller than the sun. Our replica could fit inside a machine the size of 60 football fields and would have the weight of 3 Eiffel Towers. To make it work, we'd need 2 specific hydrogen isotopes. One of them, called deuterium, we'd extract from water. The other one, tritium, we'd brew from lithium during the fusion reaction itself. We'd give the mini-sun its own magnetic field with the help of huge magnets, at least 1,000 times more powerful than those you put on your fridge. This field would keep the artificial sun in place while we're heating it up to 150 million degrees. Few materials could handle the scorching plasma of our sun. We'd have to create a robust blanket for it, one that wouldn't melt during the scorching fusion. Once we had all the engineering issues figured out, the artificial sun would completely change the way our energy system works. It wouldn't emit any greenhouse gases, and there would be no hazardous radioactive waste left to decay slowly over 1,000 years. Unlike fossil fuels, we'd never run out of hydrogen, the most common element in the universe.
So that's basically a quick recap. So thank you. Enjoy the